I'll be presenting some work I did as an undergraduate on a verified program and for frequent item set mining with Frederick. So kind of just an overview, I'll kind of introduce the problem, then talk about some of the preliminaries, and then how we formally verified it using the Coq proof assistant, and then some experimental results of the algorithm running on some test data sets. So really, what's the problem and motivation behind this? There's a lot of growing interest in justifying decisions made by these AI algorithms and how you can formally specify these algorithms, and then how can you trust that an efficient implementation of this algorithm is actually correct. And as the frequent item set mining problem is kind of a cornerstone of a lot of these other like expert systems and AI algorithms, it kind of becomes critical to prove that the implementation is actually correct. Oh. Okay, cool. So I don't know if you guys are familiar with the problem. It's pretty much the given a huge data set, find items that were bought together or that occur frequently in a set based on some kind of threshold. So the real contributions of this work was the implementation of several efficient versions of this algorithm in the Coq proof assistant, and then we also proved the termination of the algorithm, which was not done in previous work, and then we proved the correctness of all these efficient implementations with respect to a specification, and then we did some performance testing comparing this algorithm to unverified Java algorithms that solve similar stuff. So kind of a preliminary is this BMF notation, which stands for the Bird-Morton's formalisms, which is kind of just a way of writing programs in more of a mathematical term. So this would be an example of the map function. So you take a function and map it to all of the elements within a list. That's kind of how it looks more formally. And then down here, let's see if I can get a clicker. Yeah, so here would be a predicate, so this is just going to return true or false. And yeah, it might look a little complicated, but we'll work our way backwards. So it's saying that this list of visits gets filtered on another list and sees if that is a sub-list of this list of visits, and then counts the number. Counts the number, that's what this pound sign is, the length function, counts the number in that list and then compares it against this least threshold. And actually this is like the key predicate used in solving this problem. So that is in the Bird-Mertens form. Then here is actually the Coq equivalent of that code. And so we can see kind of the differences just in how you write it. So we can take this predicate and then using program calculation, which is kind of like an algebra program where you look at the program more as like a mathematical object and then mutate it with certain properties, we can actually write a specification for the frequent item set mining problem in a pretty layman's kind of term. So here we have the subs, which is a function that takes the object of list. So these are all the possible objects that it could occur in this data set, and then it creates all the possible sublists of that items, and then you can apply, this is the actual data set, so it's a list of lists of visits with a threshold, and then you apply that predicate which I told you about earlier to see which one of those lists or which one of those objects occur frequently within the list, and then you filter it on top of all of the possible arrangements of these objects. Now that is super inefficient, but it is kind of a naive solution that we will consider as a specification for this program. And then kind of going on the program calculation side of it, you can write these lemmas. So this says for all lists with the function x and it maps to a true value, then when we apply the filtering function, you're just going to get that list. Because if it's always going to be true, the list is going to be the same, if that makes sense. So using that, we can start doing these kind of algebra manipulations of the program to get a more efficient version. So we take the definition of the algorithm, or the definition of that function, break it up, and then using the definition of that subs function I was talking about earlier, then with that some of the other definitions of these previous programs, you can kind of just unfold it. And then with that property of filter, which I was telling you about, always true, so that means it's always going to return the list, you can then actually obtain a more efficient version of the program, because now it doesn't have to hit all those base cases and expand all the different, it doesn't have to pass all of those algorithms now because we have exploited the base case. So now we have actually came up with a program that is equivalent to the previous specification but is more efficient, if that makes sense, using this kind of methods. So that's just one example. Let's see. Oh yeah, so here is that specification again, which I was just showing you guys. Yeah, so that's actually one transformation that we optimize the program to be equivalent, and then we can prove that those two programs are the same. So this is the cock code for the exact same from that derivation, and you can see that now this base case when the list is empty is just much longer, but this means it's more efficient because it's not, every time it's hitting that base case, it's not doing another recursive call. Everyone following me? Okay. All right, so here would be an example of the proof, right? So we have our original specification, and then we have this improved, optimized version. And then in Coq, we can define this lemma that says, given all the possible lists of visits and all the possible object lists, applied those to two different functions, we can prove that they're equal. And then so this is what a proof would look like in Coq. And I'm not going to go into too much detail with each one of these, but it's pretty much different tactics you use to reason about this program, and then quit at the end checks that all of this, the statement you put up here, is correct. So doing that, we can do different transformations to the original program and obtain a correct implementation at the end. So we do some merging, which was the, I think I demonstrated the I demonstrated the fusion transformation, do some generalization, then the base case filtering, and then a tabulation, which is a way of memorizing previous states. And with each one of these transformations, we prove it equivalent to the previous transformation and thus have these chain of equivalent proofs. And then at the end, we actually take this version of the program and prove it equivalent to the specification. So here are some of the results. You can see that that Coq specification, it is it's infeasible really if you wanted to run that on any large data set. It's just more of we naively think that it's correct. So you can see the spec here. Here's the spec that was originally published in the WHO paper here, and there are times. And then even with that first transformation, you can see that the execution time just drops down dramatically. And so over here, each one of those FIM1 and FIM2 all the way up to FIM5 are all the different transformations applied to the program. You can see with each transformation, it gets more and more efficient and is pretty much on par with the Hue calculations. And then this FIM6 was a different tabulation function that we were trying to use to make it more parallel, but obviously there's some issues there. So yeah, this was applied across the zoo data set, which I believe is publicly available through MIT. And then also a big find, well I guess it's not that shocking, but what you use as the type within the list. So if you're using an int or an integer, that can really affect your runtime. So here's a graph just showing the different programs running on these different types with the ints, the integers, and then the just basic type that it got, or what was used. So really in conclusion, we can show the usefulness of program calculations in real world data mining, and then showing the applications of Coq in verifying these programs, and then really demonstrate that you can have an efficient version of a solution that is as efficient as an unverified solution, which is now verified. And so in the future work, we're going to probably try to make it parallel, making more so it can run on more nodes and have a more memory efficient version of the program. And then here's some references. So I don't know if there's any questions.
Anyone have a question?
Yes.
It is not really a question, but the slide before, please.
Mm-hmm.
Yes, to verify the parallel version of the program. It is what I wanted to ask you before you put your conclusion. Would be really interesting if you can succeed to do it. It's something interesting. And what I want to know, have you some ideas how you have tried to build the parallel version?
Yeah, so there is some work on it. Really, it comes down to this tabulation. If you can make this tabulation pair, which is kind of just a memorization, and it uses a tree data structure and then manipulates that tree data structure. But if you can create a way of segmenting that data structure across multiple nodes and then merging them back together, you could. That's where the parallelization is going to really take effect there.
Yes, if I understand, you can do it on a multi-computer. You build blocks, and that you allow to a multi-computer. Each computer compute the block, and then you can find a way to collect them.
Yes, yes. So that's really where the parallelization. But to do that, there's some homomorphic list kind of theory that plays into account with that. And one of the big challenges is you have to prove that parallelization is associative, which is going to be very difficult.
Okay.
But yeah, that's where most of the improvements from parallel implementation. I hope that answered your question.
So anyone else? Any question? Actually, your program is for mining frequent item sets.
Yes.
Which type of frequent item sets?
So it's
because a lot of some frequent item sets are sensitive, some are weighted. So if you mine the frequent item sets, how you decide? Because some frequent item sets are not useful. So what happened with that?
Oh yeah, so that's like kind of more based on the application use, that would be up to whoever is using it. Really, we're just trying to make the algorithm and show that it's correct with respect to this implementation.
And sometimes you are just collecting the frequent item sets and from long time. It affects on memory. How deal with the time with the frequent item set?
Yeah, that's definitely one of the future works is the memory efficiency, right? Because the program puts it all into memory, which with large data sets, that is not efficient. So that is definitely a future work that needs to be improved. There needs to be some way you can link into a database and then prove that link and change to the algorithm doesn't affect the outcome. But that is definitely a huge drawback on this, because if this program probably wouldn't run if you're unable to put the data in.
And your algorithm verified program can handle the data stream, like data is generated continuously, and we don't need all the data. We just need some frequent item sets. Can it handle with that?
So with streaming data, I'm not sure. I mean, I guess you could apply the program in some kind of iterative fashion with a string.
Have you compared with some traditional algorithms?
Yeah, actually.
Like a priori
Yes. We did compare without a priori. Those graphs are in the paper, but I forgot to throw them up here. But yeah, it was equivalent, pretty much in time to the a priori, which was an implementation. Yeah.
Thank you.
Yeah, no problem.